Just to recap what we know now, work is the transfer of energy to and from a system and is given by the formula W work equals to force time displacement cosine theta. And energy is the capacity of a system to do work. So now we're going to use those concepts. We want to develop formulas for specific types of energy using the concept of work, starting with kinetic energy. Kinetic energy is the energy of an object due to motion. So it's a potential for work that is stored in the movement of an object. And that's pretty easy to understand. I mean, a moving object can do work or exert a force, right? I mean, if you try standing in front of a train or a charging unicorn. But we want a formula to quantitatively determine how much kinetic energy an object has. And to do that, we want to calculate how much work it takes to increase an object's kinetic energy, provided that kinetic energy is the only form of energy that we're changing. So, let's start with the natural state of an object. Now imagine here, we have a ball that is flying in space with no gravity and no air resistance, right? It's just going to fly through at a velocity of vi. And that's constant because, of inertia. Now, let's make the situation a little unnatural, okay? We're going to reach into the picture, and as the ball is traveling towards the right, we are going to exert a force on it. And that force is exerted over a period of time t, over a displacement of t. So after this force is applied, the ball is going to accelerate, and the final velocity is going to now become v final. To summarize our picture right now, we have the ball traveling at a certain velocity, and then for a certain amount of distance it's going to start speeding up, accelerating, and then later on it's going to start traveling at a new velocity. And the whole entire thing about us saying that we reached in to apply this force is just saying that the environment has done a certain amount of work on the system, which is the ball. So, how much force did we exert? Well, F equals ma, right? Now, what we're going to do is we want to break down that acceleration a variable using one of our kinematics equations. And so we don't really know the amount of time it takes, the amount of time that we applied the force, so we don't know t. But we do know the displacement. And the kinematics equation without t but that has displacement in it is the following. And we want to rearrange that and isolate for acceleration to get that gigantic term over here. And so we want to replace this entire thing into our F equals ma over here. And so now we have this. And if we multiply both sides of this by the displacement, that would give us Fd. What is force time displacement? Well, isn't that just the work? Because in this case, the force and the displacement are in the same direction, so cosine theta would be cosine of 0 degrees, which is 1. So in that case, Fd itself would be equal to the work. And I'm going to expand this entire thing over here, expand this, multiply into Vf squared, and then multiply that into Vi squared. And remember, this amount of work that we have added is equal to the amount of kinetic energy we added. So we can also say that this expression here physically means the final kinetic energy minus the initial kinetic energy. The difference is the amount of work that we put in. It's not difficult to see that we have matching terms. We have this minus that, and this minus that. So we can conclude from that the amount of kinetic energy that an object has is given by this formula. And voila! So there you have it. Kinetic energy is equal to half times the mass of an object times its velocity. In this case, velocity is really just speed, because when you square it, the negative sign is going to be gone anyways. So in any direction, it should still be the same. Now this over here is actually also known as the work energy theorem. And it states that the work done on an object is equal to the change of kinetic energy if all the other forms of energy remain constant. And that's really what we've been using to develop our formula, right? So like in the video on work, if the work is positive, it means, well, your speed has increased. If it's negative, it means your speed has decreased. And that's pretty easy to get after you experiment with some numbers here and there. Now let's take a stab at graphing the relationship between velocity and work. Here's our formula once again. Now since it is a square relationship, our graph is going to be quadratic. So you can see once again that your velocity being negative wouldn't make a difference. It will still give you the same results, a positive kinetic energy. And kinetic energy really can't be negative at all. And one last thing, that square over here means that if you increase your speed, the velocity, the magnitude of velocity, by 2 times, your kinetic energy is going to increase by 4. And that's why speeding is so dangerous. Okay, I think that was pretty straightforward. I hope you enjoyed that. I'll see you next time.